Alright, so as promised last time, we're going to start on our formulas here. The first one we're going to be looking at is Kostant's multiplicity formula. And the idea behind this is to express our formal character of our finite dimensional module v lambda as a integer linear combination of certain characters of z of certain roots. Then use our previous lemmas and Harsh-Chandra's theorem to simplify. So we're going to let m lambda be the collection of L modules, for example, say V, such that for fixed lambda, first off, V is the direct sum of its weight spaces relative to our Cartan subalgebra H. Second is the action of this thing on V is by scalars given by our character function chi lambda of z for z in this for the given lambda in H star. And keep in mind that that fancy thing is just the center of the universal algebra of L, the developing algebra. And part 3 is that the formal character of V belongs to our fancy X. Belongs to, then it was this thing. Now, keep in mind all standard cyclic modules of weight lambda meet these of weight lambda qualify. As do their submodules, which it says here are not necessarily the sums of standard cyclic submodules. And we see that m lambda is closed under the operation of taking submodules taking homomorphic images and taking finite direct sums. By Harsh-Chandra, m lambda is m mu precisely when lambda is linked to mu. This brings us to our first vector. Lemma, not vector. Let V be such an algebra, an L module, sorry. And then V has at least one maximal vector. And the proof for our third condition there, for each positive root and each weight mu of v, mu plus k alpha is not a weight, of v for some large enough k, being an integer, of course. Thus, for some weight mu, no mu plus alpha for alpha positive is a weight. So any non-zero vector in v mu is then maximal. So for each lambda in h star, we're going to let theta of lambda be the set of mu in h star such that mu is less than lambda and less than or equal to lambda, and mu is linked to lambda. Recall that we saw that mu being linked to lambda means that mu plus delta and lambda plus delta are Weyl conjugate. And so for our next result, we're going to use Harris-Challenger's theorem to limit the possible highest weights of the composition factors of our z of lambda. So proposition, our setup is lambda is an h star, then part A. Z lambda has a composition series. Oops. Part B, each composition factor of our z lambda is of the form of our earlier v mu for mu in theta of lambda. Keep recalling that theta lambda is defined here above, meaning it's essentially linked to our mu is linked to lambda. And C states that v lambda, each v of our specific lambda only occurs once as a composition factor. Of our z lambda, of course. The proof for part A, if z lambda is irreducible, then z lambda is v lambda, and we're done. 1 second, sorry. If not, Z lambda has a non-zero proper submodule we're going to call V, which we know is going to lie in fancy M of lambda, for lambda being our given lambda, of course. Since the dimension of Z lambda is 1, lambda does not occur as a weight of V by our lemma, the one we just showed. V has a maximal vector, say of weight mu less than not equal to lambda. So V contains a non-zero homomorphic image W of Z of mu. As in particular, their characters match up, but by their length. Chi lambda is chi mu, so they're linked, as I said. Lambda is linked to mu. And then, by definition, mu is going to be in theta of lambda. Now consider Z lambda over W and W. Each module is standard cyclic. And lies in M lambda, but either has less weights, fewer weights right here, linked to lambda than Z lambda, or the same linked to lambda, but some of smaller multiplicity. And so we can repeat the above argument for Z lambda over W and W. So we can repeat until we bottom out by finiteness. Which is a composition series. Now, part B. We're trying to show that each composition factor is the form V mu for a mu linked to and less than or equal to lambda. So each composition factor of Z of lambda lies in M lambda, hence has a maximal vector by before. Hence is standard cyclic being irreducible. And from before, by previous results, each composition factor must be isomorphic to some v of mu. So mu belongs to theta of v, theta of lambda. And C is automatic, as the dimension of z lambda, lambda is just 1. Alright. So thus, we can write from this proposition that gives us that the character of z lambda is the character of v lambda plus the sum for some positive weights, some positive not weights in that sense, it's a bad term in this context, some d lambda, d mu, scaling the character of v mu. Summed over the mu in theta lambda, summed over, I guess I'll write this in a new line. Mu in theta lambda not being lambda itself, with lambda and h star still fixed. Order the elements of our theta lambda as pi 1 through pi t. Such that lambda I less than or equal to lambda j. I guess they're not going to be equal. The notation they use here is kind of awkward. Lambda j implies I is less than or equal to j. So lambda is pi t, the last one. By our proposition, each character of z of mu j may be expressed as an integer linear combination of the characters of v of mu I with, of course, I less than or equal to j, with, of course, the last one corresponding to lambda having coefficient 1. Thus, the resulting system of t equations has a triangular matrix relative to our order with 1s on the diagonal. And thus its determinant is 1. So we may invert it over the integers. And express each character of v of mu j as a integer linear combination of the characters of the z of mu j, mu I, for I less than or equal to j, and of course with character of z of mu j having coefficient 1. And this doesn't guarantee positiveness anymore, positivity of our coefficients, just that they will all be integers, you know? Sometimes that's, yeah. Next up, we get a nice corollary for this. Let lambda be an h star. Then the formal character of v lambda is a, yeah, this is just restating what we have. It's a integer linear combination. The sum of c mu times the character of z mu, summed over, of course, mu in theta lambda, with c of lambda being just 1. And we apply this to lambda being dominant integral, with of course the formal character of lambda being the formal character of v of lambda. Then the dimension of v lambda is finite, and the sigma of the character of lambda is just the character of lambda for all sigma in the file group. We've seen that already. Now we write the character of lambda as the sum for our coefficients above, mu times the character, the formal character of our z mu, over mu in theta lambda as above. So, by our previous lemma, the fifth lemma in the chain that we did at the end of last video, I forget what that's called, of q with ch of lambda, the convolution of q with the formal character of lambda, is the sum of c of mu times e plus mu plus our delta, by the second lemma from yesterday, at the end, sigma of q star character lambda is sigma of q star sigma of character lambda. I forgot what it's called again because my brain is fried. And this is equal to the sine of sigma times q convoluted, that's what it's called, with the character of lambda, for of course sigma being the vowel group. We also get that we can apply this to the other side, sigma of the sum of our c mu times our e mu plus delta is the sum of our c mu times epsilon of now sigma of our mu plus delta. However, since the vial group permutes the sigma plus delta transitively, with of course mu being linked to lambda, and we know C of lambda is 1. So we get that C of mu is the sine of sigma if sigma inverse of mu plus delta is lambda plus delta. Thus, and here's our key, thus we get that the convolution of Q with the formal character of lambda is the sum over our sigma in the vial group of the sine of our sigma times epsilon of sigma of lambda plus delta. By our third lemma from last time, we get that the character of lambda is Q convoluted with P convoluted with epsilon negative delta convoluted with the character of lambda, which is P convoluted with epsilon negative delta convoluted with the sum over the vial group of the sine of our sigma times epsilon of sigma lambda plus delta is equal to P convoluted with sigma of the vial group times the sine of delta times epsilon of sigma of lambda plus delta minus delta, which is the sum over sigma in the vial group of the sine of sigma times P convoluting E of sigma lambda plus delta minus delta. And this proves our theorem kostant, which states that for sorry, give me 1 second here. If we let lambda be in lambda plus, then the multiplicities of v of lambda are given by m lambda of sigma being equal to the sum over our sigma in the vial group of the sine of our sigma times p of mu plus delta minus sigma of lambda plus delta. And this, it says this does express our multiplicities directly, but in practice, if you want to like actually calculate these things, because like I said in a previous video, you can build like computer programs to calculate these, and for like high rank, the vial group is going to get really big, and so in those cases you are still better off using Freudenthal's recursive formula that we reviewed last time. And as you can probably tell, I'm stalling out a little bit at the end here because I don't want to get into the Weil and Steinberg's formula, because I think that'll make a good pair for like a video later on. And if I start Weil's formula now, it's going to take forever, so we're just going to end it here. And I know it's kind of shorter. Sorry about that, but that's just kind of how it paced itself out in this one. Anyways, I've been having problems with the internet, so keeping it short will probably make it easier to upload. My voice is breaking apart. Thanks for watching.